Welcome to lecture 24. So for 5.6, putting it together, which method do I use? We have gone over a ton of different methods for probability. So what should we use? Well, we're going to go ahead and draw the flowchart, which is from your book on page 284, which talks about the appropriate, or determining the appropriate probability to use. Alright, so the first question we're going to ask ourselves is, are you finding the probability of a single event? So are you finding the probability of a single event? Okay, so we have two options. One, our answer would be yes. The other option we would have the answer would be no. So if we're looking at yes, we have another question. Are the outcomes equally likely? Alright, so if the outcomes are equally likely, if they are, we would say yes. So then what would we do? We would use the probability of E, which is the number of our event E over the number of our sample size, or the event space. And that would be it. But if the outcomes are not equally likely, so no, what would we do? We have a new question. Is it possible to get empirical data? Alright, so if our answer is yes, then what we would do? We would use the probability of E is the frequency of E divided by number of trials. If no, then we would use subjective probability. Alright, so that was where we went with that. Now let's take a look at the next shoot off. So if you're saying, are you finding the probability of a single event? So this was the single event, yes, these are all the outcomes for yes. But if we're looking at something that does not have to do with a single event, then this is our options, or these are our options. First, new question. Do the events involve or and or at least? Okay, so we have three options this time. So we have the option of or. If it is an or statement, we have a new question, which is, are the events disjoint or mutually exclusive? So if our answer to this is yes, then we're, oops, that's a bad yes, then we'll use the probability of E or F, which is going to be equal to, let me write it below, equal to the probability of E plus the probability of F. Very simple. But if our answer is no, they are not disjoint, we're going to use the following. The probability of E or F is equal to the probability of E plus the probability of F. And remember, we're going to subtract where they are, you could say, overlapping, where they intersect. So that would be the and. So probability of E and F. Alright, so that was what we were doing for the OR statement. Let's take a look at the AND statement. So if our answer is an AND to this, then we have a new question. Are the events independent? Once again, two options, yes or no. Okay, so if yes, we're going to use the probability of E and F. I'll move to a lowercase and. Is going to equal to the probability of E times the probability of F. So if our answer is no, they are not independent, then we're going to use the probability of E and F is going to equal to the probability of E given the probability of F given E. And lastly, the at least statement. For at least, we're going to use probability of at least 1 equals to 1 minus the probability of none. Alright, so definitely a good chart to study. Okay, so we have these. These are the different options, the split-offs. The main questions to ask are always the good questions to ask yourself in your mind. Are you finding the probability of a single event? The next good question, are the outcomes equally likely? Or do the events involve or, and, or at least? Is it possible to get empirical data? Are the events disjoint? Are the events independent? Okay, these are some of the good main questions to ask yourself to figure out where you are going with your probability and for the counting. Alright, so let's take a look at example 1. In the fame show, Deal or No Deal, a contestant is presented with 26 suitcases that contain amounts ranging from 1 cent to $1 million. The contestant must pick an initial suitcase that is set aside as the game progresses. The amounts that are randomly distributed among the suitcases prior to the game, as shown in the table below. What is the probability that the contestant picks a case worth at least $5,000? What approach should we use? Alright, well, let's take a look at our flow chart to decide here. So the first thing is, are we finding the probability of a single event? Looking at this, the answer is yes. One thing's happening, they're picking one suitcase. So then we're going to go to, are the outcomes equally likely? Well, the answer to that is yes. They're all randomly assigned, so the probability is equally likely, which means we are going to use this right there. So let's go ahead and use that technique. The probability of E. And what is E? Let E be. It's worth at least $5,000. Okay, so the probability of E is going to be the number of E divided by the number in the total. So what is the number? Worth at least $5,000. So 5,000 or greater. Well, the numbers that are 5,000 or greater, or sorry, the suitcases that have amount of money in it that's 5,000 or greater would be 5 suitcases plus 7 suitcases. So that's going to be 12 suitcases total. Divided by the total number of suitcases. So adding these all up, we get 26. And that comes out to approximately 0.461. I rounded out to 462. Okay, so what does this mean? Well, if I was to translate this, let's say for translating, always make sure if you ever do any work on the side, unless it's labeled scratch work, indicate what you're doing. So that's about 0.46, which is equal to 46 over 100. So what would this be saying? Well, in about 100 different games, we would expect about 46 games to result in a contestant choosing a suitcase worth at least $5,000. So let's write that down. In 100 different games, we would expect about 46 games to result in a contestant picking a suitcase worth at least $5,000, period. Okay, so there we go with example 1. Now let's take a look at example 2. According to a Harris poll, 14% of adult Americans have one or more tattoos. 50% have pierced ears, and 65% of those with one or more tattoos also have pierced ears. What is the probability that a randomly selected American has one or more tattoos and pierced ears? What approach should we use? Well, a key word stands out to me, and that is the word and. This is saying, what is the probability that a randomly selected person has one or more tattoos and pierced ears? So let's look at our flow chart. We are looking at two different events happening. The pierced ears, the one or more tattoos, and then the pierced ears. So those are two probabilities. So we're looking in this direction. Then the question is this an or, and, or at least? And we're trying to figure out what the probability is of the person having tattoos and pierced ears. So we're looking at and. The next question is, are the events independent? Well, if you remember, some of the people who have tattoos also had pierced ears, so they were not independent events. The answer is no, they're not independent, which means we are going to go ahead and use this probability. So the probability of, so we shall use probability of E and F, but they were not independent, which means we're going to use the probability of E times the probability of F given E. So let's go ahead and name our probabilities. So let's let E equal one or more tattoos. And F is ears pierced. Oops. Alright, so what are these probabilities? Well, the probability of one or more tattoos is 14%, so 0.14, times the probability of ears pierced given that the person has tattoos. So that says 65% of those have tattoos also have pierced ears. So that would be 65%, or 0.65. Going ahead and multiplying that out, we get about 0.091. Actually, we get exactly 0.091, so we use the equal sign. So what is this saying? Well, we can just say the probability that a randomly selected American has one or more tattoo and pierced ears is 0.091. And there we go. Okay, so now we're going to determine the appropriate technique to use for objective 2. And this should say the appropriate counting technique to use. And we're going to draw the flowchart on page 286. Okay, so first thing, our first question we ask ourselves is, are you making a sequence of choices? Okay, that is the first question. So once again, we have the option of yes or no. If yes, are the number of choices at each stage independent of previous choices. If the answer is yes, we can do multiplication rule of counting. Which is just multiplying them all together, P times Q times R, and so on. However, if our answer is no, we'll use a tree diagram, which is a lot of work, but it can be done. Okay, so those are those options. Let's take a look at what would happen is if we're not making a sequence of choices. So if we're not making a sequence of choices, we have a new question. Does the order of arrangements matter? So if yes, the order does matter, we have a new question. Are you selecting n objects or only r objects? So if you're only selecting r, so less than the whole amount, we're going to use n pick r, which is going to equal to n factorial all over n minus r factorial, so the permutations. If we're going to use all n, we have a new question. Haha. Are the objects distinct? If yes, we'll just use n factorial. If no, we're going to use n factorial all over n sub 1 factorial times n sub 2 factorial, on and on till n sub k factorial. So remember, this one is like the flag problem we were talking about. You know, the 4 red flags, 3 white, and so on. We use all of the items in the group, and we're just trying to figure out the different ways to arrange. Okay, so that was the yes. So what if we said no? The order does not matter. Well, then we're going to use combinations. Order does not matter. Remember, that was the main difference between permutations and combinations, was order does not matter. For combinations, order does not matter. And that is the formula for combinations. Okay, so what are the main questions we're looking at when we are working with counting techniques? First question is, are you making a sequence of choices? If the answer is yes, our question is, are the number of choices at each stage independent of the previous choices? For example, if you think about rolling a die, each time you roll the die, they're independent. Even if you rolled the die once, that's not going to change what you get the next time. However, if you have a deck of cards and you pick one card from that deck and you do not replace it, that changes your chances of picking a card the next time, because there are less cards. One of the other questions we have is, does the order of arrangements matter? If the order matters, that'll change what probability you're going to use. Second to the last question we would use is, are you selecting all objects or only some of the objects? And lastly, a question to ask yourself when you're figuring things out is, are the objects distinct? Okay, so these are some of the good questions to ask yourself when deciding which path to take. Let's take a look at the examples. Example 3. The Hazelwood City Council consists of 5 men and 4 women. How many different subcommittees can be formed that consist of 3 men and 2 women? What approach should we use? Alright, the first question to ask ourselves is, are you making a sequence of choices? The answer to that is yes. So then the next question is, are the number of choices at each stage independent of previous choices? Well, so we're picking between men and women. So let's see. If we select from men and then select from women, the number of choices at each stage is going to be independent of the previous choices. The men chosen, it's not going to impact the women that are chosen. So we're going to use multiplication rule of counting. Huzzah. All right. So we're trying to find n of subcommittees. Which is going to be, let's see, what objects are we doing? We're talking about selecting men and women. So the number of ways to pick, 3 men, times that by number of ways to pick, 2 women. Alright, so how would we get this? Well, the number of ways to pick 3 men, let's see. We're talking about picking, so should we use combinations or permutations? And remember, we're thinking about order, so does order matter? Well, order does not matter. So we're going to go ahead and use combinations. How many men are there total? There are 5 men total, and from it we're taking 3 men. So C, 5, choose 3. Then we're multiplying that by, same thing, we're going to use combinations because order does not matter. Now for the women, we have 4 women total, and we're choosing 2 women. So C of 4, choose 2. Let's go ahead and write these out. So that's going to be 5 factorial all over, 3 factorial times 5 minus 2 factorial. Then on the top we get 4 factorial all over 2 factorial times 4 minus 2 factorial. Simplifying, we have times 3 factorial times 4 factorial all over 2 factorial times 2 factorial. This will come out to be 10 times 6, which gives us 60. So what is our answer? The question was, how many different subcommittees can be formed? And the answer would be 60 different subcommittees can be formed. So as usual, if the problem was asked in word form, you should answer in a word form, complete sentence with a period. Why a period? Well, we're in college. Hopefully we'll be getting jobs in the real world, or maybe you'll be a college professor too, which is hopefully the real world. But make sure to write your sentences as a complete sentence. It's a good habit to get into. All right. Example 4. The Daytona 500, I hope that's how it's said, the season opening NASCAR event has 43 drivers in the race. In how many different ways could the top 4 finishers, first, second, third, and fourth place occur? Which approach should we use? Alright, so let's take a look at our flow chart here. The first question is, are we making a sequence of choices? And we'll say yes. Let's view the first choice for the first place, second choice for second place, and so on. So we're going to say yes. We're talking about sequences of choices. The next question is, are the number of choices at each stage independent of the previous choices? So we can look at this as yes. Let's take a look. We have 1, 2, 3, 4 possible places. If we pick the first place person, there are 43 number of ways to pick the first person, right? Because there are 43 different drivers. Then we'll multiply that by the number of ways to pick the second driver. Well, we no longer have 43 drivers in total, right? Because the first one was taken out, which means we only have 42 drivers to pick from for second place. Then for third place, we would only have 41 drivers to pick from. And lastly, we would only have 40 drivers to pick from for fourth place. Alright, so multiplying this out, we'll get 2,961,840. And then we can label this with n being the top 4. But this is just one way we can view it. Another way we could view this problem would be for a permutation. we could say for the top 4, we have 43 and we want to pick from it 4, and order does matter, which is why we'd be using a permutation, not a combination, because order would matter in this problem. So then we would get 43 factorial all over 43 minus 4 factorial, which is going to be 43 factorial over 39 factorial. And that would leave us with, let's see, 43 is going to be 43 times 42 times 41 times 40 times 39 factorial all over 39 factorial. Cancel these values out, and we're left with the 43 times 42 times 41 times 40, which equals to the exact same thing we got from the other way we did it. So sometimes there are different methods for getting the right answer. Okay, so once again, what work should you show for your exam? I want you to show the labeling of what you're finding. As always, label your work. Show if you chose permutation, combination, if you're using one of the two. Show these 2 steps as simplifying. These steps right here, if you did it in your calculator, that would be perfectly fine. You could go ahead and just skip to the last answer. But as usual, because it's a word problem, we're going to answer in word form. So our answer would be, there are 61,840 what? Different ways that the top 4 finishers could occur. And that is it for this section. Please email me if you have any questions.